Yes, sir, you can begin with the session, sir. So,
Yes, sir. Good evening, all. Once again, we are here to learn the discrete mathematics and combinatorics. So far, we are done with the 1, 2, 3, 4, 5, 6, 7. In last lecture, we learned graph algorithm, unit number 9. Now, in today's lecture, we are going to learn unit number 10, that is number theory. So let's quickly go through the content of number theory. So in this particular unit, we are going to learn the basic, that is divisibility and primes. So in divisibility and primes, we have Euclidean algorithm and fundamental theorem of arithmetic, then congruence and modular arithmetic, congruence and arithmetic, modular arithmetic. So in this, properties and solving the linear congruence, Chinese remainder theorem. So basically, in Chinese reminder theorem, we will go through this statement, proof and application of Chinese reminder theorem. Then we have formats Little theorem and Euclidean theorem. Then public key cryptography. So in public key cryptography, specifically RSA algorithm, key generation and encryption and decryption. The last part of this unit number 10 is application of number theory. And there are number of fields where we are going to use number theory. But as per the syllabus, specific related with the cryptography and random number generation. Okay. Yes, let's start with the unit number 10. So unit number 10 is number theory. And what is number theory? Let's understand first what is number theory. So number theory is a branch of pure mathematics devoted primarily to study of integers and integer value function. Guys, whenever we are going to say the number theory, so specifically in number theory, what we are going to learn, the study of integers and integer value functions. Okay, basically it deals with the properties of this number theory and the relationship between the numbers and especially properties of the natural numbers and positive whole numbers. Yes. So the special stress is given on the, if you are going to study the properties of this number theory, so we are going to learn the properties of natural numbers and uh, positive whole numbers. Okay. So it's not just about adding, subtracting. It's about something inventing, that is discovering the hidden rules that numbers follows. So like why some numbers can only be divided by 1 and themselves. Yes. So we know. So numbers which is divisible by 1 and that number itself, which is that number we are going to learn. Okay. Or figuring out the puzzles and the pattern that numbers form. Yes. So it's specifically natural numbers or integers, which are the patterns. Patterns. Yes, specific patterns are there, numbers which is divisible by 2, cube of cube root, then squares, likewise patterns if we find in the integers or whole numbers. Okay. So guys, whenever number theory is the number theory word is there, so it is basically theory related to the study of integers and the function of integers. Okay. Moving ahead, divisibility. So what is mean by divisibility in terms of mathematics terms? So we will learn divisibility and the primes, that is prime numbers. Okay. So divisibility, if there are two integers or there are two numbers, like for example, if you consider A and B. So if A and B are the integers and there is some integer, one more integer like C. So we have total three integers, so A, B, and C, such that A equals to B into C. A equals to B into C. Then we say that B divides A, or A is a factor or division of A, and we are going to write this as a B by A. B by A. So divisibility, when how we define divisibility, we are going to consider the three numbers. Basically, A and B, two integers, and one more integer, that is C. And how we are going to represent these three integers in the form of equation, right? So A equals to B into C. Then we are going to say that B divides A. B, integer B, divides integer A, or A is a factor or divisor of A. B divides A, number one, or is a factor or divisor of A. And how we are going to represent this? How we are going to write this? B by A. Okay, B by A. So an integer A which is not equals to 0 means value of integer is other than 0. Okay, so an integer A not equals to 0 divides B. Again, B is an integer. So already we know the representation of this divisibility. So A by B. If there is an integer K such that B equals to AK. So for firstly, how we define, and in second statement, again, same terms we are going to define. Okay. Just instead of that C, we took here K. So you can take C or K or any letter. Okay. So an integer A which is not equals to 0 divides B such that A by B, how we are going to represent A by B, if there is an integer, one more integer, that is K, such that B equals to AK. So again, in previous definition, we wrote A equals to B, BC or B into C. Here, we took one more integer. Instead of C, we took K. And how we represent this? B equals to AK. So divisibility. Then second term is prime or prime numbers. Yes, guys, we in school days we learn what is meant by prime numbers, right? So same definition we are going to learn here. We know what are the prime numbers. But it is an integer, right? So it is divisible by that number, right? And uh, positive numbers and itself. Okay. So one and that number itself. Okay. Yes. So definition for primes or prime number. A prime number is an integer greater than 1. Yes, it should be a greater than 1 whose only positive divisor are itself and 1. Yes. As we know, whenever we are going to define the prime, so that number, particular number is prime number when that number is divisible by, or divisors are itself that number only and 1. Okay. So other way, a positive integer in general, how we are going to define the primes. Okay. A positive integer, prime numbers is nothing but it is a positive integer. So here we consider in general P, which is greater than 1. A positive integer P greater than 1 is called a prime number if the only positive factor of P are 1 and P. What is P, guys? In second definition, we are going to consider the number. Okay, so instead of specific number, we have considered here P. P is a prime number. When that P is, or the only positive factor of that particular number P is 1 and P, that number itself and 1. Basic condition, that number should be greater than 1. That number should be greater than 1 means 2, 3, 4, 5, 6. So these numbers we are going to consider whenever we will define the integers, sorry, primes. Okay. So in other way, a non-prime number greater than 1 is called as composite number. Yes. So other than this prime number, that is non-prime number, greater than 1 is called as composite number. So yes, other than prime numbers, the numbers which we have, that is nothing but the composite numbers. Okay. So we will understand with the above example. So see here, example, we have, for example, 15. Okay. So 15 is here. Okay. So before this example, let's understand this basic fundamental theorem of arithmetic. Okay. So for this prime number, if I consider a particular number, for example, 3. Okay. Does 3 is a prime number? As per the definition, a prime number is an integer greater than 1. Yes, 3 is greater than 1, whose only positive divisors are itself and 1. Yes. So 3 is divisible by 1 as well as that number, that is 3 only. Okay. Yes. So that is nothing but the prime numbers. Likewise, take any number. Like if I consider 5. So does 5 is divisible by itself, means 5, and it is divisible by 1? Yes. If I consider, guys, 4. Does 4 is a prime number? 4 is divisible by 4. But other than 4 and 1, does 4 is divisible? Yes. Other than 4 and 1, it is also divisible by 2. So 4 is not an prime number. Okay. Yes. Moving ahead, the fundamental theorem of arithmetic. Okay. Fundamental theorem of arithmetic. So what it says, every positive integer greater than 1 expressed as a product of primes and their representation is unique up to the order in which the factors are written. Yes. So fundamental theorem of arithmetic says the every positive integer which is greater than 1, which can be expressed as, how it can be expressed? It is a product of primes, that is prime numbers. So it is a product of prime numbers and this representation is unique up to the order in which the factors are written. Yes, guys. So prime numbers is a positive integers, right? And in basic fundamental theorem of arithmetic, what we are going to say, it is greater than 1 and it can be expressed, product means multiplication. Product of prime numbers, yes, it is a product of prime numbers and this representation is unique up to the order in which the factors are written. Yes, factors, yes, guys. So number of factors we can able to find out. Okay. So with example, we will understand. So every positive integer can be written, as the product of primes, that is prime numbers, where the prime factors are written in order of increasing size. Yes. So from smallest to largest, So in this order, we can able to write the factors of these numbers. Okay. Yes. So see, in this example, we have number 15. Okay. So factor of this 15. So what is factor, guys? The number which is multiple of that numbers, right? Factors. So you see here, 15 is the number and multiple of this 15 is, so 3 and 5. 3 and 5. These are the two numbers which are multiple of this 15. So if we, in the table of 3, so 3 5s are 15, right? And in the table of 5, 5 3s are 15. So this 3 and 5 are the two factors of this number 15. These are the two factors of 15s, right? So as per this definition, fundamental theorem of arithmetic, as per this definition, every positive integer greater than 1, yes, 15 is greater than 1, expressed as a product of prime numbers and this representation is unique up to the order in which the factors are written. So with second definition, again, we will get the clarity for this fundamental theorem of arithmetics. So every positive integer can be written as the product of primes. Yes. So positive integer 15 we have in first example, and this can be written as product of prime numbers. Yes. So this 3 and 5. So product of these two prime numbers where the prime factors are written in order of increasing size. Yes. So whenever we are going to write, we are going to write in increasing order. So first 3 and then 5. So 5 is greater than 3. Let's check with second example. So second example, number is 48. As per the fundamental theorem of arithmetic, how we are going to represent this? It is the product of prime numbers, right? So it is the product of prime numbers. So factors, first we need to find out the factor of this number 48. So we know 2 into 2 into 2 into 2. So 2 raised to the power 4, as we are multiplying 2 by 2 4 times. So 2 into 2 into 2 is 2 raised to the power 4 into 3. So 2 raised to the power 4 means 2 into 2, 4, 4 into 2, 8, 8 into 2, 16, right? So 16 into 3, sorry, 2 into 2, 4, 4 twos are 8, and 8 twos are 16. Yes. So 16 into 3. So one more prime number, that is 3. And we wrote this in increasing order. We wrote in this increasing order. So can we represent this like 3 into 2 into 2 into 2? No. As per this definition, every positive integer can be written as the product of primes. Yes. So these prime numbers we are going to write in product form 2 into 2 into 2 into 2 into 3, where the prime factors are written in order of increasing size. Yes. One more. So factor of this 17. So factor of this 17. So 17 is divisible by 17 only. 100. So factor of this 100. So 2 into 2 into 5 into 5. So 2 twos are, or 2 raised to the power 2, that is 4 into 5 into 5, 25. So 25 into 4. 25 fours are 100, right? So again, these 2 and 5 are the factors of 100, and it should be written in increasing order. So 2 into 2 into 5 into 5. So 2 raised to power 2 and 5 raised to the power 2. So 2 square into 5 square. Last example for this fundamental theorem of arithmetic. Again, we have 28. So first, to represent this 28, we need to find out the factor of 28, right? So factor of 28, 2 and 7. So in the table of 2, we will get 28, and in the table of 7, we will get the 28. Okay. So increasing order, yes, 2 into 2, 14, 14. So sorry, 2 into 2, 4, 4 into 7, we got 28. Okay. Yes. So guys, as per this definition, we wrote or we represent the positive integer in terms of product of factors, and it should be in increasing order or increasing size. Okay. So this is fundamental theorem of arithmetic. What it says, every positive integer can be written as the product of primes, product of prime numbers, where the prime factor are written in order of increasing size. Yes, guys, now moving ahead, least common multiple. We learn this in schools, least common multiple, then greatest common divisor. All this we learned in schools. So let's quickly revise. What is this least common multiple? The least common multiple of positive integers. For example, if these integers are a and b, is the smallest positive integer that is divisible by both a and b. What it says? Least common multiple. A least common multiple of positive integer. These integers, let's consider a and b, is the smallest positive integer that is divisible by both a and b. Now, this least common multiple can be denoted by how we represent this LCM. How we represent LCM? So, we denote the least common multiple of a and b by just we are going to write LCM short form and first number comma second number. So what is this first number and second number? So these are the factors which is or in the table of these factors we will get the number that is least common multiple. Okay, so this with this example you will get the clarity. LCM least common multiple. So LCM of 3 and 7. How we need to find out or how we are going to find out the least common factor, least common multiple of this 3 and 7. So it is the number which is multiple of this both two numbers, that is 3 and 7. Let's check. So in the table of 3, do we get 21? Yes. So in the table of 3, we have 21. So means 21 is multiple of 3. Second number, that is 7. So does in the table of 7 we have 21, means 21 is multiple of 7? Yes. 7 threes are 21, right? 3 sevens are 21. So LCM of these two numbers, 3 and 7, is 21. So let's see, as per this definition, does um, this example is satisfying or not. So LCM, least common multiple. The least common multiple of the positive integers a and b. According to this example, a and b are 3 and 7. Is the smallest positive integer? Yes. That is divisible by both a and b. Yes, just now we checked these two numbers, right? 3 and 7. And this LCM, that is 21, is divisible by 3 and 7 both, right? So 3 sevens are 21, 7 threes are 21. One more example, LCM of 4 and 6. LCM of 4 and 6. So it is the least common multiple of these two numbers, 4 and 6. So how we are going to calculate, or how we are going to find out least common multiple of these two numbers, that is 4 and 6. So first multiple of 6 is 12. Does this 12 comes into the table of 4? Yes, 4 threes are 12. So least common multiple, least. Okay. Can we have 24 LCM as a LCM of 4 and 6 as 24? No. As term suggests, LCM is least common multiple. Okay. So in the table of this, both the numbers 4 and 6. So 12 is multiple of 4 and 6, both the numbers. Third example, LCM of 5 and 10. LCM of 5 and 10. Yes. So LCM of 5 and 10 is 10. Does this 10 is multiple of 10? Yes. 10 ones are 10. 5 is multiple of 10. So 5 into 2, that is 10. So in this way, guys, these three examples which we learned, this satisfy the definition of LCM, least cost multiple. So least common multiple of the positive integer, any two integer which we need to find out, or for that two numbers which we need to find out the least common multiple. A and B is the smallest positive integer that is divisible by both A and B. Okay. Yes. Now second, that is greatest common divisor. Greatest common divisor. Let's understand. Greatest common divisor. There are two numbers, and these two numbers are integer numbers. So let A and B are the integers, and both the numbers are non-zero. Means these numbers are not zero. The largest integer D such that the largest integer D such that D divided by A and D by B called the greatest common divisor of both A and B. Numbers A and B. Okay, let's with the example we will understand this. Okay, so greatest common divisor as per the definition. So the greatest common divisor of integers both A and B is the largest positive integer which divide both the numbers that is A and B. Okay. So the greatest common divisor of A and B is denoted by GCD, short form like LCM, least common multiple. So how we represent it? LCM and LCM of two numbers. Likewise, GCD, that is greatest common divisor of the numbers. So numbers A and B. Now let's understand GCD with example. So GCD, what is the GCD of two numbers that is 48 and 72? 48 and 72. Let's check as per the definition. Okay, so this answer we are going to get is correct or not. The positive common divisor of 48. The positive common divisor of 48 and 72 are. So divisor of this 48 and 72. Just list out this. Does 48 is divisible by 1, 2, 3, 4, 6, 8, 12, 16, and 24? Yes. So for 24 twos are 48, right? 16 threes are, 12 fours are, right? Likewise, all these factors are positive factors of 48. Similarly, 72, yes. So 1, 2 factors of 72, 1, 2, 3, 4, 6, 8, 12, 16, and 24. Again, just check with these factors, 72 is divisible or not. Okay. So what we got, guys? So positive common divisor of this both the numbers, that is 48 and 72. So positive, yes, and common divisor, right? Common divisor of this both the numbers. So 1, 2, 3, 4, 6, 8, 12, 16, and 24. These are the common between this 48 and 72. So these all numbers will divide both the numbers, that is 48 and 72. So now we got the common divisor of both the numbers. Now we have to find out the greatest common divisor. So among this divisor, which one is the greatest? Yes, obviously 24, last number, right? 24 is the greatest number. So that is the answer for GCD. So GCD of this 48 and 72 is 24. Okay, so greatest common divisor. So as per definition, the greatest common divisor of integer A and B is the largest positive integer which divides both A and B. Yes, 24 divides 48, 24 divides 72 also. Okay, so this is the greatest common divisor of this 48 and 72. Likewise, in example number 2, greatest common divisor of 19 and 72. So the only positive common divisor of 19 and 72 is, yes, 1, guys. 1, right? So we don't have other than 1, which is the common divisor of 19 and 72. there is only one number, that is 1, which is the common divisor of 19 and 72, right? So 1, there is only one number, that is 1. So 1 is the GCD of this both the number, that is 19 and 72. I hope guys both the concepts are clear. Least common multiple, least common multiple. So the LCM is the positive integer, right? Which is divisible by both the numbers for which we are going to calculate the LCM, right? And then second one, greatest common divisor. So in this, we are going to find out the common divisor of both the numbers. And among these common divisor, the greatest number which we have among this common divisor, that is the GCD of these two numbers. Okay. So now we understood with the couple of example, LCM and GCD. Now guys, next concept is Euleridian algorithm. And for which purpose this algorithm is used? Euleridian algorithm, a method or algorithm to find the greatest common divisor of two numbers by repeated division. Okay. So this Euleridian algorithm says it is a method or a algorithm to find GCD of two numbers by repeated division. Yes. So the Euleridian algorithm is used to find out the greatest common divisor of the numbers. How? By repeated division process. So the Eulerian algorithm gives a method or algorithm for finding the greatest common divisor of any two positive integers. So with this algorithm or with this method, we can able to find out the greatest common divisor of two numbers. Okay. So basically for which purpose it is used? To find out the greatest common divisor. This Eulerian algorithm is used. Now next is congruence and modular arithmetic. Congruence and modular arithmetic. So modular arithmetic, if a particular number which is integer. Okay. If a is an integer and n is positive integer. So we have two numbers, that is a is which is integer and n is also a positive integer. Then a mod n. How we write guys? Mod with two parallel lines, right? A mod n is the remainder obtained when we divide a by n using the Eulerian algorithm. Okay, so Eulerian algorithm is used to find out the modular arithmetic. How we define this? A particular number a and second one number, that is n, is an positive integer. Then a mod n is the remainder obtained when we divide this a by n. Okay, so when we divide this number, integer number, that is a by n, okay, that is called as, which is equals to remainder obtained by dividing this positive integers by n. Second term, that is congruence. Congruence, again guys, this term we heard in schooling. Okay, congruence. How we are going to define this congruence? If we have again a positive numbers, so any positive number, for example, let's consider n is an positive number and two integers, say a and b, are said to be congruent modulo n if they both have same remainder when divided by n. When divided by n. And how we are going to define this, or how we are going to write this? A congruence b mod n. This sign is used to read as congruence. A congruence b mod n. Okay, so definition for congruence. If n is a positive integers and two integers a and b are said to be a congruent modulo n if they both have same remainder when they divided by the n. And how it is represented? A congruence B mod n. Okay. Yes, now guys, properties of this congruence. Okay. So properties. So these are 1, 2, 3. These three are the properties. Okay. So we can define this addition, subtraction, and multiplication of modulo n, because it is easily seen that if A congruence B modulo n and C congruence D modulo n, then how we write? First is for addition. So A plus C congruence B plus D mod n. For subtraction, A minus C congruence B minus D mod n. The third property is for multiplication. A into B congruence B into D mod n. So guys, these are the three properties of congruence, which are for addition, subtraction, and multiplication. Addition, subtraction, and multiplication. Oh, next concept is Chinese remainder theorem. Chinese reminders theorem. What this theorem says? The Chinese remainder theorem states that a system of simultaneous congruence defined by pairwise co-prime positive integers, that is n1, n2, up to so on, nk, and arbitrary integers a1, a2, up to so on, ak, such that how we are going to represent x congruence a1 mod n1, x congruence a2 mod n2, likewise, and up to so on. Last term, that is ak, that is an nk, we are going to use to represent x congruence ak mod nk. Okay. There exists a unique solution x modulo n, where n values are different n values, that is n1, n2, n3, up to so on, nk, that satisfy all the congruence simultaneously. Yes. So this Chinese remainder theorem says, the Chinese remainder theorem state that the system of simultaneous congruence defined by, how we define? Pairwise. So pairwise positive integers, if we consider n1, n2, up to so on, nk, then arbitrary integers a1, a2, up to so on, ak. And how we are going to represent this? X equals to a1 mod n1, x equals to a2 mod n2, likewise x equals to a3 mod n3, and up to so on, x equals to ak mod nk. So there exists a unique solution x modulo n. So this common terms for this x modulo n that satisfy all the congruence simultaneously. Okay. So Chinese remainder theorem. Okay. Next is the basic application of this Chinese remainder theorem. Number one, it is used in cryptography. You might have heard this term, guys, cryptography in networking. Cryptography. We will learn out what is meant by cryptography. Okay. So timing. So this is the first application of Chinese remainder theorem. Number one, that is cryptography. Number two, error detection. Yes, this theorem is used for detecting the error also. Okay. Specifically in terms of computer. Okay. So in terms of cryptography, we use in computer field error detection. Yes. In computer field, we use error detection. So specifically in networking, we will be able to learn in detail this cryptography, error detection, parallel computing, and last one, that is quantum computing. Okay. So these are the four application of what? That is Chinese remainder theorem. So Chinese remainder theorem is used in cryptography, error detection or error correction, parallel computing, and quantum computing. quantum computing. Okay. Yes, let's understand the term that is public key cryptography. Public key cryptography. So in this public key cryptography, let's understand the term first, cryptography. What is cryptography? Okay. Yes, we heard this term in networking. So whenever we need to pass data from source to destination, right? So guys, it must be transferred securely, right? From source to destination. Otherwise, so if it is not secure, the hacker will hack your data. So if it is sensible data, for example, in banking system, so you use the authentication like username and password, then the certain amount, right? So which amount you are going to transfer from source to destination. So all are the sensible things, right? So we don't want to hack these things, right? So we are going to use the cryptography, secure transmission of data from source to destination, secure transferring of data from source to destination. There we are using cryptography. Okay. So in bookish terms, cryptography is the discipline of encoding and decoding the messages. Yes. So as I said, cryptography is used to transfer data from one location, that is source, to other location, that is destination. While sending this data from one location to another location, we are using encoding and decoding. Okay. Encoding, in short, guys, converting your message or your data into cryptic, means crypted form, right? So what is encoding or how it is done, we will learn. Then once we send this encoded data, right? So how we are going to generate encoded data? Some logic we use to convert this plain data into encoded data, so that while transferring this data, no one can able to understand, or even though it will get hacked, we cannot, or hacker cannot able to understand what is this data related about. Okay. So in short, encoding, converting plain data into some specific format, that is encoded data, and other end, this encoded data will get received. Okay. So at source, it will get converted, plain data will get converted into encoded data, and at destination, so this encoded data will get received and it will get decoded. It will get decoded so that this destination will get the original message or original data. Okay. So cryptography definition, guys. Cryptography is a discipline of encoding and decoding the messages or information. Okay. So cryptography is used in banking system. Yes, as I said, in banking system, we use sensible data and we need to transfer this data from source to destination, including the ability to use ATMs and to do online banking would collapse without ability to securely transmit financial information over the public network. Yes. So in banking, what we do, we transfer the data, sensible data over the public network, specifically transaction related data, right? Okay. So while sending this data, we use cryptography. What is cryptography? Converting this data into encoded data. Then encoded data will get traveled to the destination and it will get decoded so that original message will get received by the destination, right? So related with cryptography, we have few terms like cipher. What is cipher? Cipher is a method of encoding the messages. Yes, just now we understood what is encoding. Okay, but cipher is the method for which encoding encoding the messages is nothing but the cipher. Plain text, yes. So add original text. Plain text refers to the original text that is being encoded. Yes. So the data, original data, which we need to transfer from source to the destination, that is plain text. Okay. So on plain text only, we are going to convert this plain text into encoded data. Then we have C4 text. What is C4 text? C4 text refers to the encoded message. Yes, encoded data. That is C4 text. Plain text, C4 text, right? Then encryption. What is encryption? Yes, the process of encoding a message is sometimes referred to as encrypting or encryption. Yes, so this is encryption is the process of encoding a message or data, and this is known as encoding. So guys, these are the terms, right, which we use in cryptography. C4, it is the method or process to encode the message or information. Plain text, that is original message. C4 text, which is encoded message or encoded information. Encryption, it is the process of converting data into encoded message. Okay. Then description. Description, yes, we just now understood what is description. It is the process of decoding the message. In some is sometimes referred to as deciphering or description. So by description, right, what we will get? We will get the original message which is transferred by the source. Okay, yes. So these terms which we need to understand in cryptography, that is C4, plain text, C4 text, encoding, or sorry, encryption, and then description. Okay. Yes. Now moving ahead, one more term, that is Caesar C4. Caesar C4 or Caesar. Yes. So Caesar C4 is one of the earliest known C4 and was used by Julius Caesar. Caesar or Caesar. Okay. So this is the name of that person, right? So with this name, this Caesar or Caesar. Okay, Caesar C4. So each letter in the message is simply replaced by the letter coming three letters after it in the alphabet. Yes. So what is Julius suggests? Whenever we are going to encode, right? So this letter will get replaced by the letter which comes after three letters, right? Caesar C4, Caesar C4. So this person suggested that the each letter in the message is simply replaced by the letter coming three letters after eight in the alphabet, right? So this is called as Caesar C4. So let's understand with the example. Okay, example says if we have these three letters X, Y, Z, as per the Caesar C4, what we have to do? We have to replace these three letters X, Y, Z by the letter which comes after these three letters. Okay, so first letter, that is X. So after X, number one, Y, Z, and again we are going to the original, that is A. So Y, Z, and A. Third letter is A. So in this, X will get replaced by A. Likewise, Y, again third letter. After Y, we have Z, right? Then A, and then third letter is B. So in this example, Y will get replaced by B. And then third letter, that is Z, will get replaced by, after Z, A, B, C. So C is the third letter. So as per this definition, Caesar C4, so whenever you will have the letters, so these letters will get replaced by the letter which comes after the three position, okay, or third position letter will get replaced the original letter. Okay, so I hope guys this example understood. Likewise, if you have ABC, so ABC will get replaced by, so after A, we have B, C, D. So A will get replaced by D, then B. After B, we have C, D, and E. So B will get replaced by E. Then third letter C, so D, E, F. So C will get replaced by F. So likewise, if we use this Caesar cipher, then every letter will get replaced by third letter. Okay. So yes. So in public key, just now we understood this example. In this example, these letters are replaced by the third letter. Okay. Now moving ahead, we may make this somewhat quantitative by assigning a numerical value to each letter. Yes. So if we assign numerical value to this all A to Z alphabets. So 0 for the alphabet A, 1 for alphabet B, likewise 2 for C, then 3 for D, likewise till 25 is used to represent Z, right? So earlier letter is replaced by letter on. Now we use this 0, 1, 2, 3, 4 numerical digit or quantitative to represent this letter A, B, C, D. So if we let P represent the numerical value of given letter in the plain text and C represent the number, it is replaced by in C4 text. So now we have C. So how we read this, guys? Yes, already we learned here. In yes, here congruence, right? So congruence, how we represent in this with three parallel lines. So C congruence B plus 3 mod of 26. Now this will get decoded. This will get decoded, right? So here we got plus 3. It will get decoded by minus 3 so that original message can be received. Okay. So P equals to, sorry, P congruence C minus 3 mod 26. Now, in general, how it will get represent? We might use shift other than 3. Yes. So other than 3, we can use general letter also, right? By general letters, we can able to represent this. So let's see congruence P plus B mod 26 for some other integer, that is B. Now, we might mix these things up a little more. Yes. Now we instead of that digit, we use common letter, that is B. Now again to mix this, C congruence A P plus B mod 26. So such cipher would be called as affine cipher. Affine cipher. Okay, guys. Yes. So one more term, that is affine cipher. Already we learned the few terms related with the cryptography. One more term, that is affine cipher. Now to decode this, we could try to solve the congruence for P in terms of C. Now proceed as follows. So C congruence A into P plus B mod 26. Then again, this term, that is AP, will comes to the left hand side. AP congruence C minus B mod 26 and P congruence A minus, sorry, A raised to the power of 1. That is A raised to the power minus 1 C minus B mod 26. So guys, in this way, we can in general decode and we can first encode and then we can in general decode also. Okay. So encoding and decoding. Now one more term, that is hill zipper. One more term, that is hill zipper. So hill zipper, blocks of letters are encoded simultaneously rather than encoding letters separately in a method similar to an append zipper. Okay, guys, just concentrate here. Here we replace by letter, right? In affine zipper. Then in next, that is hill zipper. Here, block of letters will get encoded simultaneously rather than encoding the letters separately. So here in affine zipper, we have encoded single letters, right? Single letters. But in hill zipper, we are going to replace the block of letters. We are going to replace block of letters. Okay. So that is called as hill zipper. Understood the difference between Affine zipper and Hill zipper. Affine zipper, here individual letter will get replaced. Okay, that is encoded and then it will get decoded. In Hill zipper, a block of letters will get encoded and then it will get decoded. Okay, so Hill zipper block of letters are encoded simultaneously rather than encoding the letters separately in a method similar to an affine zipper. Okay. So block of two letters. Now consider here we have two letters P1 and P2. Corresponding encoded letters C1 and C2 would be the determined by formula. So this block of letters will get replaced or the encoded. So C1 that is uh, congruence. Okay, C1 congruence A into P1 plus B into P2 mod of 26. Likewise, C2 we are going to encode in Hill zipper. So C2 congruence CP1 plus DP2 mod of 26. And this A, B, C, D. So these are nothing but the integers which we use to encode the block of letters. Encode the block of letters. Now moving ahead, guys, in public key cryptography, we have algorithm that is RSA algorithms. RSA, you might have heard this RSA algorithm. Okay. So how this represent, why we are saying this is RSA algorithm? These are the name of three human being, right? So the R represent the Reviest, S represent the Shamir, and A Adelman. Okay, so this 3% discover this RSA algorithm, right? So that is why in short form RSA. Okay, Raviest, Shalimir, and Adelman. So algorithm is an asymmetric or public key cryptography algorithm, which means it works on two different keys. Okay. So this RSA algorithm works on two different keys, that is public key and private key. So we will understand, guys, what is meant by public key and private key. Time being, let's understand this RSA algorithm. RSA algorithm is an asymmetric or public key cryptography algorithm, which means it works on two different keys. Number one is public key and number two is private key. Now, what is meant by public key encryption? So public key is used for encryption and is known to everyone, while the private key is used for description and must be kept secret by the receiver. Guys, in RSA algorithm, we use two keys. Number one, public key, right, which is known to everyone. Means if I am the sender, so if I know the public key, so I can able to encrypt the information or encrypt the data with the help of public key. So it will get transferred and then with the help of secret key, description will get implemented by the receiver or the destination. Okay. So RSA algorithm is named after, yes, we know this three persons, Revius, Adi Shemir and Leonard Adelman, who published the algorithm in 1977. So this algorithm, RSA algorithm, comes into picture in 1977. Okay, and these are the three persons who has invented or published this RSA algorithm. Okay, now let's understand the RSA algorithm, and in RSA algorithm, how we are going to encrypt and decrypt the data. So already we understood in RSA algorithm, we encrypt the data with the help of public key and we decrypt the data with the help of private key. So example, if person A wants to send a message securely to a person B, then to encrypt the data, A will use the public key, and to decrypt the data, B will use the private key, right? So see here, person A encrypts the message using person B's public key, and person B decrypts the message using their private key. So in RSA algorithm, two keys are used. One is public key, which is used for encrypting the data. Second one, that is private key, which is used by the destination for decrypting the uh, data or information. So keep in mind, guys, public key is available to everyone, but private key is with destination person. Okay. Yes. So RSA algorithm is based on the factorization of large numbers and modular arithmetic for encrypting and decrypting the data. Okay. Yes. So it consists of three main stages. Factorization. So key generation. First, in RSA algorithm, first key will get generated. What is meant by key? Yes, we just now we learned public key and private key. For which purpose these keys are used, we learn. So first steps or first stage in the RSA algorithm, creating a public and private key. Second stage, encryption. Yes, with the help of this uh, public key, we are going to encrypt this data. So sender encrypts the data using public key to get the ciphertext, and then ciphertext will travel in the medium, right? So at the end, description is done, and descripting the ciphertext using private key to get the original data. So these are the few steps: one, two, three. Generating a key. Second, encrypting a data. And once it get encrypted, it is known as ciphertext. Ciphertext will travel in the medium, and then this ciphertext will get converted into original data, that is known as description. Okay, decryption. So application of number theory. So guys, these are the general application of number three. Number one, cryptography. Yes, we just now understood the cryptography. So in cryptography concept, we use the number theory. Okay. Second one, data security. Yes, for data security, number theory is used. Then computer science and algorithm. Yes, in computer science, as data will get travel from source to destination, right? So this number theory is used. Then coding theory and error correction. Here also number theory is used. Computer graphics uses this number theory. Financial mathematics and cryptocurrency. This also use the number theory. Okay. So these are common application of the number theory. Now specific as per the syllabus, we have two terms. Okay. So for number one, application of number theory in cryptography. Application of number theory in cryptography. So now, just now we understood the concept of cryptography, right? So cryptography, converting the original messages into ciphertext, and ciphertext will get converted into the original message, right? So application of number theory. Number one, cryptography. So modern cryptographic algorithm for data and communication security are based on number theory. Yes, the basic concept of which govern the field. Yes, guys, with the help of number theory, which we use in cryptography, so secure means it will get generated, means with the help of cryptography, ciphertext will get generated, and this ciphertext will travel securely along with the medium, and then it will get converted into uh, original message, right? So concepts such as prime numbers, modular arithmetic, and discrete logarithms are the ones underlying billions of cryptographic encryption and description method. Yes. So these prime numbers, modular arithmetic, discrete logarithms, these are used while implementation of the cryptography. And yes, example. Yes, just now we learned the RSA algorithm. So in cryptography, we have RSA algorithm, which is the application of number theory. So RSA algorithm commonly used in the data encryption system involves the theory of numbers, and it is through the employment of prime numbers such as public key as well as the private key that are used for encryption and description of message are generated. Yes. So guys, first application of number three, that is cryptography. Specifically in RSA algorithm, we use encryption and description of this Then second application of this number theory is random number generation. Guys, number theory is used in random number generation. So random number generation, yes, we need to use this concept in cryptography itself, generation of random number. Number two, Monte Carlo simulation. Number three, gaming and gambling. Number four, cryptography and security. So number theory application, generation of random numbers. Okay, so in cryptography, we generate the random number. So cryptography used to generate a secure key and initialization of vectors, ensuring that encrypted data remains secure. And if pseudo-random sequence is predictable, hackers can break the encryption. Yes. So to avoid this, we are going to generate the random numbers in cryptography. Then second one is Monte Carlo simulation. Yes, maybe you heard this term, Monte Carlo simulation. Okay. So in science and finance, random numbers are generated using the number theory to model complex systems. Yes. So to model the complex system, we are using this Monte Carlo simulation, such as evaluating the risks in financial derivatives or calculating the high dimensional integrals. Guys, simulation in short, so Monte Carlo simulation suggests that the system will get generated, specifically complex system will get generated in small model so that risks will get reduced, specifically in terms of financial models or the any general model. Okay. So this is the second application of number theory. Gaming and gambling. So digital casinos and video games used to create unpredictable events and such as card shuffling and slot machine outcome. So here also number theory, that is random number generation, is used. And last, that is cryptography and security. Yes, so number theory plays a significant role in creating unpredictable random numbers for security, ensuring that the encrypted data and sensitive information are protected. Yes, so with the help of random number generation in cryptography, we can securely transfer the data over the networks or the medium to receive the original data. Okay. So guys, these are the two specific application of number theory as per the syllabus, that is cryptography, and second one, random number generation. So guys, overall, all the topics of this unit number 10, that is number theory, we have covered. Guys, is there any difficulty related with any topic of this number theory? Any term which you don't understood? No?
Dear learners,
Okay.
any doubt you can ask, or we can conclude the session here. I think, sir, learners are not having any doubt. Thank you so much,
Okay.
sir, for conducting such a wonderful session for learners. And you have explained the practical applications of this entire thing that is very much required to understand for the learners. So thank you so much, sir. And thank you so much, dear learners, for joining. Good night, everyone. Take care.
Good night, sir.
Good night, sir.